Alright, so in the previous video, we saw the rigorous definition of limits of functions using epsilon and delta. And today we are going to use that definition to prove some limits. Okay, for example, we have to show that the limit of f of x minus 3 is 2 as x approaches 1. So let's see how that can be done using that definition. So let us first recall that definition. What the definition says is that if epsilon is any positive real number, then we have to prove that there is a positive real number delta such that if these inequalities are true, then this inequality is also true. That is, if the distance between x and 1 is less than delta, but of course x is not equal to 1, then the distance between f of x minus 3 and 2 is less than epsilon. So we will now have to choose an arbitrary epsilon positive, and for any such epsilon we have to prove that there is such a delta for which these things happen. Okay, so let epsilon greater than 0 be any real number. In other words, let epsilon be any positive real number. But how can we possibly guess what such a delta is? For that, we have to start from this inequality and do a kind of back calculation to try to get something like this. From there, we will have to figure out what delta possibly can be. So let's see. Ideally, this back calculation I should not say ideally, but there is no need for this back calculation to be a part of this solution itself. But because our aim is not presenting something formally, but rather understanding the thing, so let me just do the back calculation here itself and not as a rough work. So we want this to happen. But this inequality is equivalent to this, which in turn is, you note carefully that I am writing equivalence here, okay, logical equivalence, not just mere implication. This, and that in turn, because 5 is positive, is equivalent to this. So comparing this and this, you can clearly see that in place of delta we can just take epsilon over 5. So if delta is chosen to be equal to epsilon over 5, then the first thing we notice is that of course delta is positive because epsilon is positive, and 5 of course is also positive. And the second thing is this, then implies and at the same time x is not equal to 1. X is not equal to 1 I am writing because otherwise this difference would be 0, but it's given that it should be greater than 0, or if that is the case, then we have this. However, just now we have seen that this inequality is the same as this inequality. That's why I was using equivalence, so that you, in doing your back calculation, you not only have a way of going from here to this, but you can come back also. And in place of this, so we can now write okay, but that's what we wanted. Hence, as x tends to 1. So this we have proved, rigorously proved. In the next example, we are going to establish two important but rather trivial limits, again using our definition. You may notice one thing before I write this fourth example, that here things have been particularly easy, as if things have been arranged in such a way so that we do not have to put virtually any effort in finding delta. We just carelessly go with the flow and delta drops out as a consequence. This won't be the case always, okay? It is just merely like this in this example to show us at least how to find delta somewhat easily in this case. But now the complicated examples are coming. So we need to verify these two limits. X naught is some real number and B this, where K is some constant. Again, that means it's some real number. So the first function here is the identity function and the second function is some constant function. Again, let epsilon greater than 0 be any real number. Then in this case, the things are so easy that there is no need to do any back calculation. You will realize what. For delta, I am choosing epsilon itself here, and that of course is greater than 0. Oh, I needed to write for. For this delta, we have implies, note that here the function is the identity function, so the x value itself is f of x and the limit L is x naught itself, and by our choice of delta, this is epsilon. So that's it. This is what we need to show in this case. Hence, we have this limit, And part B is even easier because here nothing changes at all. It's the constant function. Let you will have to write this sentence so many times in dealing with these problems that you will quickly want to shorten it like this. It's understood that epsilon is some arbitrary positive real number. That's it. It's enough to write like that. Then for in this case actually any delta works, but for the sake of being specific, let me take delta equal to 1. We have implies, okay, so what is the functional value here? K. And what is the claimed limit? Also K. So this difference is 0 and that definitely is less than epsilon. Hence, this is equal to K. These two limits have been established fine, and you can see that they are rather trivial, but they can be used to establish some other limits of polynomial functions. We will come to those things afterwards. Okay. Now, in the next example, we are going to make things slightly more complicated than that first one, that is the third example. And in this example, showing a limit is not our main aim, but rather a specific value of epsilon will be given. We will be required to find a delta for that epsilon. So here the limit is this, the claimed limit square root of x minus 1 is equal to 2. This is the claimed limit, and we are not being asked to prove this limit. Okay. Instead, we are given epsilon equal to 1, and in the process of finding a delta for any epsilon, this is just one value of epsilon. For this specific epsilon, we have to find a delta. So let's now see how the calculation goes. The complicacy arises because of that square root. In some other parts of mathematics, when a function is given, its domain is also given along with it. In calculus, however, when a function is given, only the formula is given, and it's assumed that the domain is the natural domain of the function. That means the largest set of real numbers, the largest subset of the set of real numbers for which the function makes sense. So in this case, the domain is this set, this interval. You cannot make x less than 1, because then you will have negative real number inside radical, and that will not be a real number. So x has to be at least 1. So it's understood that x is coming from this set, and as a result x minus 1 is a non-negative real number. So with that understanding, let us start our calculation. So again, we want this time this to happen. right? Now this is equivalent to these inequalities. Now you add, oh, I think, am I writing it correctly? Yeah, it's okay. -1, 2 plus epsilon. However, you are given that epsilon is 1. So actually this is 1. And this is 3. Now let us just take squares throughout, and we will afterwards see what we have done. Is it okay to come from these inequalities to these inequalities? Yes, because all the things that you see here are non-negative real numbers. Even the x minus 1 under the radical is also non-negative. So squaring will preserve the inequalities. I mean, they won't get reversed or anything like that. But can you go from these inequalities to these inequalities as well? Because we are writing equivalence, it's not merely implication. Yes, you can, because 1, 3 and root x minus 1, these are also all positive real numbers in fact. That is why. So if you now add 1 throughout, then you get this. However, we want to figure out the difference between x and 5. So we subtract 5 from all the quantities. That gives me this. But from this now, how can we figure out a delta? Let's see. Note that if delta is equal to 3, we will come to this issue. Okay, suddenly how I am choosing delta to be 3, we will come to that. But let's see what happens if delta is 3. If delta is 3, then what do we get from these inequalities? This implies, you see, this time we need not write equivalence, because that's not what the definition demands. The definition demands that starting from these inequalities, we have to get something. Okay, we need not go back from that thing to this. And along with that, x is not equal to 5. Alright, so this part we are getting. X minus 5 needs to be greater than minus 3, we have that. But we want x minus 5 to be less than 5. But if it is less than 3, then automatically it's also less than 5. And now using these equivalences in place of these inequalities, you can write this one. Less than epsilon, but that epsilon of course is 1. Okay, so we are getting what we want. However, what is this delta? And how is this value of delta being chosen from this situation? Here the thing is this. because you are using absolute value, right? So you need to choose that number which is closest to 0, so that when you choose that, you see among 5 and minus 3 is closer to 0 than 5 is. So that's why if our distance is 3, okay, which is the distance of 0, the origin from minus 3, if that is the distance, then on this side also you will have a room of that length 3. On that side also you have a room of that length 3. But then automatically the larger number also behaves well with this situation like this. If you can go only that far on either side, then of course the other number is also taken care of. Whether it lies on that side or this side, it does not matter. So that is why in general, if you after going through such a series of calculations, if you come across a situation like this, x minus whatever less than b, then your choice for delta can be conveniently this. We are using absolute value because we don't know whether this a and b are positive or negative. They can be anything, okay, both of them can also be negative. That condition is also possible, but delta of course has to be positive, so that's why we are choosing this, and this of course will be greater than 0. I mean, you have to choose it that way. So this is the trick that we will use in figuring out delta in this type of calculations. In that calculation, in the first one, that is in example 3, things were so symmetric and so nice that we did not have this type of asymmetry, that minus 3 on this side. This boundary is 3 units away from the origin, whereas that right boundary is 5 units away from the origin. So that kind of asymmetry was not available there. But in general, you will have to deal with such asymmetry, but you can deal with it like this. Okay. So here this example ends. These calculations of course do not prove that our limit, that means the limit of this function is 2 as x approaches 5, because for that you need to work with a general epsilon, not just epsilon equal to 1. But that was not our aim. Our aim here is to figure out the delta for that given epsilon. Okay. So now let us make the situation even more complicated by working with one such example, but not a fixed value of epsilon. Example 6. Prove that the limit of f of x as x approaches 2 is 4 if this is the function f. If x is not equal to 2 and 1 if x is equal to 2. Although this function is partly defined, I mean for 2 its value is 1 and elsewhere its value is the square of the input, but immediately right at the outset there is a simplification, because you recall that in a limit what goes on at this point where the independent variable is approaching does not matter, and in fact that is why we have this. In that previous limit, although we did not establish it, but still assuming that that is true, x is approaching 5, but the limit has nothing to do with x being equal to 5. In fact, that's why you see we keep having this condition. So that means just like that here also, what goes on at x equal to 2 does not matter. I mean, it is there, fine, the function has value 1 when x is 2, but that has nothing to do with the limit. So actually we are just working with the function fx equal to x square. Okay, that is the thing. But anyway, let's start by choosing epsilon. Let epsilon be an arbitrary positive real number. Now we want, here what do we want? Again, that same thing. We want for this to happen. This, however, because at the same time x is supposed to be not equal to 2, it is equivalent to this. Here you can just simply write, since x is not equal to 2. But now if we simply go on with the calculation, there will be a point where we will have to make further assumptions. Okay, till this it's okay. Simple algebra, 4 minus epsilon. But now itself, when we take square root, that will require this. If 4 is greater than or equal to epsilon, because otherwise you will have a negative real number inside square root, and that will disrupt the calculation totally, will make things meaningless. So that means this is something that we are assuming. Okay, we are going to assume. However, you need not write it here itself that we are assuming. You keep in mind that we want these things to happen. We are not saying that they are happening. Okay, that part will come afterwards. After we choose delta, then only that part comes. So here we are just simply seeing what we want and then translating that into something else, which is something else but equivalent to what we want. Now, according to our rule for choosing delta from that previous example, we need to choose the minimum of the absolute value of this and the absolute value of this. However, due to the present situation, we can decide what the signs of these numbers are. Okay, and as a result, we can get rid of absolute values like this. Now, note that epsilon of course is greater than 0. This implies what? 4 plus epsilon is greater than 4, because these numbers are both positive. You can take square roots on both sides, the inequality will stay the same, won't get reversed, and that gives you this. That means this number on the right side is positive. Also, minus epsilon is less than 0 because epsilon is positive. So 4 minus epsilon is less than 4. This implies square root of 4 minus epsilon is less than 2, provided 4 is greater than or equal to epsilon. Because we have not yet made any such assumption, we have to write this, and that implies this number is negative. So this is positive, but this is negative. And now we make our choice of delta. Choose delta to be the minimum of the absolute value of this. Because this number is negative, the absolute value is this. And the absolute value of this, but this is positive, so we choose this. Definitely this is greater than 0. Wire, but now we cannot get around this fact that we have to assume this. Because otherwise it becomes meaningless. Then, if we use this value of delta, actually, are we going to get what we want? Let's see. This implies minus delta is less than x minus 2 is less than delta, along with x not equal to 2. Okay, now something. I am now going to write something extra along with these inequalities, and then I will justify. So here what I have written besides these inequalities is that the negative of this, that is root 4 minus epsilon minus 2, is less than or equal to minus delta. That means that lies to the left of even minus delta, and delta is less than or equal to this. Where are these things coming from? Of course, you can guess that they are coming from this fact that delta is this minimum, but exactly how? You can understand why this inequality is coming. Delta being the minimum of this number and this number is by definition less than or equal to both of them. In particular, delta is less than or equal to this, so that's what we have written there. But at the same time, delta is less than or equal to this. But that means what? Minus delta is greater than or equal to minus of this, that is this. and this is this inequality. Okay. And now if we forget about this minus delta and delta, we then have this. Okay. And the calculations that we did there show us that these inequalities are equivalent to our final thing, that is this. I forgot to write this. You continue this, or if you want you may choose to not write this as well, because it's understood that in finding that limit x is not equal to 2. Now it's tempted to write hence the limit is 4 and we are done, but that would be wrong. That's because our epsilon here is fine, it's positive, but actually we are not looking at all the epsilons. We are looking at only these epsilons. But what about the other epsilons? They also have to be handled, no? Because for any epsilon positive, we have to show that there is a delta. We have, however, here the calculation for only this type of epsilons. But before we go to the other epsilons which are greater than 4, let me see a specific value of epsilon, and for that value, let me see what the delta is. Note that when epsilon is equal to 4, that is covered in this condition. Okay, if epsilon is equal to 4, then what is delta? Delta you can see from here, we can calculate. Delta is the minimum of, so this will be 0, that means 2, and what is this? Square root of 8 minus 2, which is 2 root 2 minus 2. It is something. Okay. Now the fact that one of them of course will be less than the other, but we need not even know that. We just know that for this specific value of epsilon, this delta works. In other words, let's give it some other name, that is say delta prime. For we have this. Less than 4, because that value of epsilon you can have here for this specific delta prime. And now we are going to handle those epsilons that are greater than 4. Now if epsilon is greater than 4, then for the above delta prime, that is this delta prime, we have less than 4, and since 4 is less than epsilon, so this is also less than epsilon. So that means you see that this situation automatically handles the other epsilons as well. And now finally we can say, hence, because now all epsilons have been handled, that the limit of f of x as x approaches 2 is 4. This finally has proved this limit. It looks complicated, it is somewhat complicated, and this prompts us to prove general theorems which tell us, those properties of limits, so that we get rid of having to do all such work every time we encounter a limit. And let us now see one of those properties, namely the sum of two functions and their limit. We have already come across that. That is, if you have two functions which approach two limits as the independent variable approaches the same point in their domain, then the sum of them approaches the sum of the limits. Okay, that thing. In most of the situations where you have to calculate a limit or show a limit, we will use properties of limits, and we will rarely use this kind of going to the actual definition and starting everything from scratch. So using the definition to prove theorems, it's given as an example. So it's just this: if the limit of f of x as x approaches c is, say, L, and the limit of g of x as x approaches c is m, then prove this: L plus m, using the actual definition, that is, which uses epsilon and delta. It can be done like this. This is not very complicated. So first of all, we have to of course choose epsilon. And now it is given that these limits exist. So for this value of epsilon, each one of them will give us a delta. Then again, by definition, there exist delta 1 and delta 2, both positive, such that implies the difference between f of x and L is less than epsilon, of course, but we do a trick here. Instead of writing epsilon, we write epsilon over 2. You can think of it as a new value of epsilon, because anyway, whatever we are writing here should be true for any positive real number here. So we can choose epsilon over 2 in place of epsilon, a new value of epsilon, say epsilon prime. For that epsilon prime also there should be some delta. Let delta 1 be one such delta. And the reason for this trick will become apparent now when we combine these things. and this. So we can similarly make the distance between g of x and m also less than epsilon over 2 by choosing x in this way. For that there is some delta 2. Now let delta be the minimum of delta 1 and delta 2. You will see that in this kind of arguments you always go for a minimum of some given number of positive real numbers. Then delta obviously is positive again, because delta is either delta 1 or delta 2 and both of them are positive. And for this we have, if now our distance between x and c is less than delta, then automatically it's both less than delta 1 as well as delta 2, because delta is the smallest, the smaller one among them. And so if you now look at the difference between f of x plus g of x and L plus m, then this difference can be rewritten as a sum. Like this. F of x minus L plus g of x minus m. And now you use the triangle inequality that is there in the system of real numbers. Thus, absolute value of a sum is less than or equal to the sum of the absolute values. Alright, and those two numbers here are this and this. However, because this as well as this is true, this is less than or equal to epsilon over 2, actually strictly less than epsilon over 2, and this one is also less than epsilon over 2. So we have ended up showing that there is such delta for which if these inequalities are true, then the distance between this new function and this new real number is less than epsilon. But then by definition of limits, L plus m is the limit of the sum. And now you understand why we chose epsilon over 2, just simply to have epsilon here. Okay, so that's it, that proves this limit. And in a similar manner, one can also prove the other properties of limits, although some of them will take more effort than this much. And this in fact concludes this section itself. After that we have the exercises which we will solve in the community posts. And tomorrow we have ring exercises from Galleon. So that will also come in community post. So see you tomorrow with that. Until then, this is me, Lucifer from Mathematical Room. Have a nice night.